The lab number 16, the ABM eval with the wired input. In this lab we will make the eval part. Just select the part vsim for input. Connect the symbols like VSTIM, 0, eval, R, param, voltage marker. So first is the vstem, eval, R. Connect the parameter R and the voltage marker. Connect all the grounds. This will be the rectifier circuit. So the value in the eval is the block which gonna implement the rectification of a sine wave. Now we have to define the value of the sine wave for the input. The R is the load resistance, and the block is gonna do the functioning of the rectification. Now go in the as a parameter and select a variable gain, because as this is we're gonna implement a function, we need to define the gain, and we want to construct the graphs in according to the gain. So I have a new row as a gain over here and give the initial value equals to 1. So we have that the gain is 1. Now this is for the creation of the sine wave as an input. We're gonna generate a sine wave with 0 offset, give number as sine 10, analog sine, and the offset should be 0, the amplitude should be 1 volt. So 1 volt amplitude and the frequency will be 10 Hz. So insert offset value of 0 and the amplitude of 1 volt. The peak value should be like 1 volt, positive 1 volt, negative 1 volt, and the frequency should be at 10 Hz. Save the file as stm.emd, so that this file will be saved at .stl. That's a sine wave like 1 volt peak to peak. Now in this circuit we're gonna have a expression for the property. The expression we have to make a V input percentage, so we have to like average ABS and change it to ABS V percent input percent negative star gain. So this should be multiplied by the absolute value of whatever voltage at plus input and minus input is multiplied by gain, and AB is absolute. Now set up a transient simulation. So we only to display the value. Press OK. the new simulation should be like in a lab 16 16_1. That's the first part of the lab. Now we're gonna form a 0.5 final transient time domain analysis from runtime to 0.5 final time, and the maximum value should be 0.001 step size. So 0.001 is my step size. So that's gonna be the I run the simulation. The display should be the sign and implementation. The analysis now connect the circuit of a .stl file for the source, because if we don't connect this, then there will be no supply or source to the eval. Run the simulation. Put the red one as input, as a green one as an output. So the red one is the input and the green one output, means that output is the half wave rectifier. Full wave rectifier. Change the gain value of 2.5. See how the gain will be multiplied with the ABS value. So there will be the change in the graph accordingly. See the graph, red one is input. So red one is input and green one output. So gain from 1 volt it increased to 2.5 volt. This is the lab 2. In this lab we will create a circuit as we have done in lab 1. And now we will connect that's a ABS thing to the reference voltage. The reference voltage is needed like an application like voltage divider, differential between like a 2 nodes, and the current is passes through a device in expression of an ABM device. In this example you will see that even though there is no input connected to the ABM symbol, it still functions. This is extremely useful if the output of the device is dependent upon more than just an differential voltages. So that's the powerful tool of eval and G value. It gives more powerful, flexible, and just add an R2 resistor voltages. So that's the powerful tool of eval and G value. Just add an R2 resistor to our source. This will lead to formation of the source and short both the inputs. Assign an net alias the input and output. So this is gonna form a input circuit for lab 2, and edit the expression as we are doing it. The expression will be changed to the absolute value be input just start again. So and run the simulation. You will see the results. In this lab, the lab 3, we will study the E reference part. So we're gonna make circuit, like a low pass filter implementing, we just use the frequency lookup table. The input to the frequency lookup table will be the voltage at the node input. The output will be at node output. The table's value describes a low pass filter with a response of like 1 for 1 means like 0 dB of frequency, like below 5 kilohertz, and a response of 0.001 minus 60 dB, which will be above 6 kilohertz. The phase lags linearly with the frequency. So we are gonna make a lookup table for 0 0 0 5 kilohertz 0 to minus 5 kilohertz, and output we see from the other end. So place the circuit as we are doing, just an AC source, load resistance, and the block. We have to do is just do like a connect circuit, and we will change the expression. Like we are giving the input to the positive terminal of the input, taking output from positive terminal of the output. The negative input or the negative output is grounded, and we're gonna see the impact on the graph. Now we're gonna give a sine wave as we do it in the expression. Edit the property of the block. In this there is a table 0001 megahertz minus 10 to 90. Now change this one value to 5 kilohertz 0. So this means that as the table's value describes a low pass filter with a response of 0 dB for frequency below 5 kilohertz and response of 0.001 like minus 60 dB above 6 kilohertz. So this will be the delay necessary to the impulse response is casual, that is the impulse response have no significance real component before time 0. That's the frequency lookup table we are forming. 000 5 kilohertz. The first meaning of this is that below 5 kilohertz it will not let it to pass. So this means that below 5 Hertz the response is 0, and above 6K the response is minus 60K. So this is lead to the formation of the low pass filter. So 5 kilohertz will be filter out. So that's how we make a like a low pass filter to become changing the value of the block. 5 kilohertz filtered out. Okay. Now, like set up the new simulation profile, and AC sweep for linear noise like 0.5. Total points like 101. Starting frequency you should take from 1K, ending like a 10K. So we are dealing between the 5K and 6K. So start from 1K and go to up to like 10K, so that we can see the clearly the all frequency which we are using in the lookup table. So set up the marker, go in the advanced. There will be marker for particular dB or magnitude of voltages. place the marker at an output node. So that's what the point where this will display the output in the simulation in the dB voltage form. So run the simulation, because so that's a dBV output. So frequency at 5 kilohertz or before 5 is 0, they are filtered out, and after 5 and above 6 the response is 60 dB. Lab 6, stained homosexual voltage controlled oscillator. Now in this lab we want to create a voltage controlled oscillator by using the E value and G value parts. We're gonna form the E value as, and we have form a like circuit like VCO. The top portion of the circuit is like a time domain function for sinusoidal source. It normally has an equation like a sine 2 pi into bracket FCT plus V input. Place the eval and component as shown in the figure. This is very important part, because in many a times we need to implement a function like in application of the controllers, application of specific mathematical equations. So by using this kind of the evals and gvals, we can construct and implement integration or differential or whatever mathematical function we want to implement with the incoming input signal. So this lab will show how we can implement a formula called y of t equals to sine of 2 pi fct plus phi t. As we know, the yt is the output and the input is coming, and it's multiplied by 2 pi, which is a constant, plus the phase changing pi, and then it's all come in the sine phase and it generated as the output. That's gonna be shown. Just connect a one sine source to the G-val, connect an RC circuit at the output. IC equals to 0 over here, and output is also connected to the common ground. The original circuit should be connected to the reference ground. So first of all, we have to connect the circuit as shown in the figure. We are doing it. Make the net alias CTRL and for the linear voltage control oscillator, we found that the FD, the frequency, is directly proportional to the controlling voltage. So the controlling voltage is like VCTR. So VCTR is the circuit which gonna give the output as a 2 pi K1, the integration of V voltage control T with the derivation of time. So the CTR circuit is generating a controlling voltage, and this one controlling voltage will be used for the generation of the all full wave sine 2 pi f t plus v integration. So this one is the function, and function for the G1 is the K1 VCTR1U. So this one is the controlling voltage VCTR. In the lookup table, add one more parameter K1, 1 mega ohm. FC is a 1 mega. Oh shit. Do it as I'm showing in the figure. As you can see in the manual, though, form the block as we're gonna use this on this value. So analog behavior modeling. Now in the stimulus, go through the circuit. Like we want to have a sine wave. Change the access setting. change the access settings. Like minimum resolution of 0.001 micro. So up to like 5 microseconds, it should be like 1 megahertz. So make 1 megahertz and 2 megahertz for the next 5 microseconds. So make it like